I'll start with an apology to my CHEM100 class. I got my wires crossed and repeated the lecture today, the 26th of January, during our regular class period on Chapter 2. We had already covered Chapter 2 last Thursday. So since this Thursday is supposed to be a review, what I'm going to do is go ahead and record the lecture on Chapter 3 and post it and let you guys know, because I want to keep us on schedule. I don't want us to run a day late just because I made a mistake. So first things first, I'm going to go share the PowerPoint for Chapter 3. There we go. And I'm also, one moment, let's back up. What I need to do is lock this meeting so I won't be interrupted. Okay, now we're going to share that screen again. No. All right, there's matter. Actually, the recording I did for Chapter 2 is better quality. So I'm going to replace the Chapter 2 version in Blackboard with the Chapter 2 that we did today. And then I'm going to create this Chapter 3 lecture right now and have it posted as soon as possible. So let's start the slideshow. Here we go. Now we're going to talk about matter today. What is matter? This is the same definition that I was given in grade school, and it still holds today. Anything that occupies space, has volume, and has mass, which is a measure of substance, is matter. So that covers pretty much the whole universe except for vacuums. And there's some argument as to whether vacuums are actually empty anyway, but we won't go there today. Matter usually, under normal circumstances and under not so extreme conditions, exists in 3 states: solid, liquid, gas. And this is an artist's representation. We'll notice that the solids are usually regular structure. Not always, but sometimes regular structure, but they're very close together. The molecules, the atoms, whatever the case may be, they're very close together and they interact closely. So much so that a solid will retain its shape and retain its volume without any help. Liquids, however, can retain their volume, but they will not retain their shape. They need a vessel to hold them, and they assume the shape of the vessel. Now, the basic difference between the two is that solids, the molecules or atoms, don't move except to maybe vibrate, right, in place. Whereas liquids are free to move and flow past one another. They still interact, but not as strongly as in solids. And then gases, if you add enough energy, then a solid will convert to a liquid, and add more energy, quite a bit more energy, then liquids will convert to a gas. Now these are physical changes, right? The identity of the substance, the matter, has not changed. We're just breaking bonds that hold the different molecules or atoms of the substance together. We're not breaking any molecular bonds that hold the structure of the substance together. So when you get a gas, notice that there's a lot of room in here. Distance between the molecules of a gas very far apart and very much higher velocity. So most of the energy in the gas is contained not in vibration, but in linear velocity until they bang into something. Okay, I mentioned that earlier. Examples: ice cube, diamond. Right, diamond's a solid. An iron bar is a solid. Those fit the definition. Liquids. Examples: gasoline's a liquid, water's a liquid, alcohol, blood is a liquid. So there's really not much confusion about those general categories of phases. This is just to illustrate that a liquid will acquire the shape of its surroundings, of its container. Gas has neither fixed volume nor fixed shape. So when you put a gas into a vessel, it assumes the volume and the shape of the vessel. Helium's an element, oxygen's an element, air is a compound. In other words, you combine, actually air is a mixture of different elements and compounds, but it's still a gas. Okay, what's a physical property? A physical property is a characteristic of matter that can be changed, if we so desire, without changing the identity of the substance. And a property is a static characteristic, such as stating the matter. I mean, what's the state of the matter? Is it a solid, liquid, or gas? That's a property. Or if we say the temperature of the liquid is 28 degrees centigrade, that's a property. We haven't done anything to change, and the property stays the same as long as we don't introduce any change to it. They're generally observable characteristics that we can see, feel, smell sometimes. Other examples: is there an odor? Is there a color? What's the volume? These are physical properties. The state we mentioned, the density, we talked about in chapter 2. Melting point and boiling points, those are physical properties. They're static. They don't indicate any change. Chemical properties, however, while they may be static as properties, they indicate the potential for a change of identity of the substance. For instance, if we say wood is flammable, then that's a property. It indicates that wood can burn, but there's no change yet. We just say that's the potential for wood. It possibly could burn. And if it does, then that chemical property changes. The identity of the substance changes. That's a good statement. These characteristics describe the behavior of matter that is possible. Flammability, corrosiveness, rusting of steel, digestion of food is a chemical property of our digestive system. So this would be ethyl alcohol is a boiling point at 78 degrees centigrade. That's a physical property. The hardness of diamond, a physical property. Sugar ferments to form ethyl alcohol. It can ferment. That's a chemical property. We're changing a substance from sugar to ethyl alcohol. Okay? A physical change is just that. It describes a change of physical characteristic. It describes the actualization of a physical property. So if we say the boiling point of water is 100 degrees centigrade at sea level, then we apply heat to water and it actually boils. We are transferring a physical property into a physical change. Okay, we saw this slide earlier. These are the three states of water. You know, solid is an ice, liquid we normally call water, and gas we normally call steam. We haven't changed the identity of the molecule. It's still water, no matter what the phase is. So that is a physical property of water to be in these different states. And the transition from one state to the other is a physical change. Now, we can change the identity of the substance with a chemical change. Example, the Bunsen burner in the laboratory. Natural gas flows in, mix it with air, apply a little heat, and it changes from methane and oxygen to carbon dioxide and water. The identity of the products entirely different than the reactants. Another possibility, we take water and pass electricity through it. We can break the bonds of water from this structure, or we may write it this way: 2 hydrogens, 1 oxygen, and we may end up with hydrogen gas and oxygen gas. Okay? Now that's not a balanced equation, but it shows the chemical change that has occurred. So what is common to all chemical changes? Bonds must be broken. The bonds that hold this water molecule together must be broken. Now, very often, new bonds are formed in the process, as they were here, because remember when I gave you the periodic table with the red boxes around those elements, I want you to learn them and the symbols, and there are a few of them that exist in the environment naturally as diatomic molecules. So these, when you write that, that's not the way hydrogen is at 1 atmosphere pressure and room temperature. That's the way it is. And it's composed of 2 hydrogens bound together. Okay, so in order to go from here to here, we broke bonds and then we reformed bonds. And this is an artist's conception of what has happened. How about chemical versus physical change here? Pulverizing rock salt. Have we changed the identity of a rock salt? No, we just made the particles smaller. That's a physical change. Burning wood, I mentioned that earlier, that's a chemical change. When wood burns, the change is chemical. The flammability of wood is a chemical property. It's static. Only when it actually burns are we describing a chemical change. Dissolving sugar in water, physical change. You still got sugar in the water. Melting a popsicle, you just change the phase. That's it. It's all physical. The only chemical change in there is burning of wood. Fermenting to ethyl alcohol, that's a chemical change. If we melt iron, we're just changing its state from solid to liquid. That's a physical change. Combining iron with oxygen to form rust, that's definitely a chemical change. You're forming bonds there. Now, what's an element? An element is any substance, it's matter, and if we take a sample and we keep subdividing it, breaking it in half, 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 eventually we get down to individual atoms. Now, if the substance was pure to begin with, it's just one element, then all atoms are exactly alike. And they can be broken down by physical means. Now, if we have compounds like water and we want the elements, then we need to use chemical means. But the element is characterized by a single identity. All the atoms in an element are the same identity. Examples: iron, aluminum, oxygen, even though it's diatomic, and hydrogen, they're all elements. And the smallest part of an element is an atom. Now, what's a compound? A compound is a combination of elements bound together into a single unit of some kind. Now, in order to have a compound, you must have at least two different elements, two or more elements. If you have atoms bound together and they're the same element, then you don't have a compound. You still have an element. So it requires two or more different elements to make a compound. Water's an example, carbon dioxide's an example, table sugar's an example. It has to have different elements to be a compound. Now, once we've established the identity of a compound, then it doesn't matter the source of the compound, how you get to that point. Whether it's by combustion, where you break something apart and you end up with a compound like water. Right? If we take, for example, if we take methane and combine it with oxygen, we'll get reactants and products, carbon dioxide and water. They're different identities, so a chemical change has occurred. But let's focus on water. Okay, water's origin here was from the combustion of methane and oxygen. But we can also do this. And let's see. I'll show you what that means down the road. This is the same, this is water. It's the same compound as that water. It came from a different source, but it's still the same identity. Right? It doesn't matter where it came from, as long as you have the same elements bound together the same way, the same structure, then the compound is the same no matter where it comes from. As the same composition. Okay, how many of these are compounds? Well, let's see, we have two elements there, compound. Two elements there, compound. 1, 2, 3. Two different, they're all compounds. Yeah, they're all compounds. Now, what's a pure substance? Well, a pure substance can either be an element or a compound, and as you break it down, so you subdivide it into smaller and smaller and smaller and smaller pieces. If it's pure, then once you've used all your physical means to reduce the compound to an individual part, a molecule, then all the molecules that you have obtained from that substance will be the same. That's a pure substance. So if it's water, pure water, all the molecules are water. If it's pure gold, all the atoms will be gold. It's a pure substance and an element. Same composition. And besides being elements or compounds, they're always the same throughout. Water, carbon dioxide, hydrogen, gold, all pure substances. Now, why do we bother identifying pure substances, besides the fact that pure gold is nice to have? Well, once we've identified pure substances, then we can talk about mixtures of those pure substances, which is the dominant form of matter in the universe, is a mixture. So two or more pure substances together will make a mixture. Mixtures can have variable composition. In other words, this mixture might have sugar and water together, right? But it could be lots of sugar and a little bit of water, or just a little bit of sugar and a lot of water. While we have two pure substances that went together to make it, the amount of each can vary. So wood's a mixture of different types of, say, cellulose, lignin. If it's still wet, it's going to have water in it, various other things. Wine is a mixture, has ethanol and water, and it has various other compounds like anthocyanins in red wine that make it turn red. Coffee, right? It has water, of course. If it's just black, then it'll have various extracts from the coffee bean, right? One of those would be caffeine, maybe, if it's caffeinated. And those components, those things that go together to the mixture, can again be separated by various physical means, because we don't change the identity of those parts of the mixture. So we're just talking about physical changes here, if we separate them. Now, mixtures can be subdivided into two categories. The homogeneous mixture is one in which we can sample the mixture various places, and every place we look has the same composition, the same amount of pure substances together makes a homogeneous mixture. For instance, if we have a glass of sugar water, if we take a smaller sample out of here, and then we take another small sample out, another one out, and we analyze it, we find that it has exactly the same amount of sugar ratioed to water every time. That's a homogeneous mixture. Homogeneous mixtures have another name. They're called solutions. Okay? And it doesn't have to be a solid dissolved in a liquid like sugar water or salt water. Solutions can be any different type of phase. You can mix two liquids together, which is what we do in gasoline, is what we do in various forms of alcohol for consumption. Right? You look on the side of the bottle, this bottle might have 15% alcohol. This bottle might have 70% alcohol. But those are solutions. Gases can be solutions. In fact, all mixtures of gases are solutions. Every one. Mix two pure gases together, you always get a solution. And it makes sense. Remember that earlier picture? The molecules in a gas are very far apart. So there's room for everybody. They basically don't interact much. So you put two gases together, they just mix, and that's it. You got a solution. Okay, example, air around you. Even solids like alloys of metals can be solutions. Brass is an alloy of copper and nickel. Sometimes various other additives, but predominantly copper and nickel. It's a solution. Now, you can't mix them together as solids. They just won't go. You have to heat them up, melt them, mix them, and then let them solidify, and you're still a solution. Okay. The other possibility is a heterogeneous mixture. And the heterogeneous mixture, depending on where you sample it, will have different composition. They will not be uniform throughout. This example is sand and water. So the composition of sand and water varies depending on whether you just stirred it up or you let it settle. Okay. Oil and vinegar don't mix. So you can mix them by vigorous shaking, but if you wait long enough, they will separate. And as they separate, they produce regions of differing composition. So let's see if we can identify homogeneous mixture. Okay, problem-solving technique, test-taking technique. When you see a question, when you've identified the question, work to eliminate possibilities. So we work backwards. These have to be mixtures. In order to answer the question, they've got to be mixtures. Pure water is not a mixture. Throw it out. Copper metal, not a mixture. It's a pure substance. Throw it out. So now all we have to do is decide gasoline, jelly beans, soil, which are homogeneous. Gasoline is a solution of octane and various additives. It is homogeneous. Jelly beans. If you look at a jar of jelly beans, you even reach in and grab a sample, 2 handfuls, and you count the colors, you find that this hand has a different ratio of colors than this hand. So that's heterogeneous. And soil, take my word for it. I've got a PhD in soil science. Soils are heterogeneous. They're not uniform mixture throughout. In fact, if you dig a pit and you scrape it smooth so you can see the various layers of soil, you see that soil has stratified. And even within the strata, the mixture of particle sizes varies from place to place. So really the only homogeneous mixture in here is gasoline. Now we can use physical techniques to separate mixtures, and it's based on physical properties. So if we want to separate something based upon the boiling point, we employ a process called distillation. We heat something up, and the more volatile component of the mixture comes off first. When moonshiners make their brew, they have to distill the mash to get the ethanol out of it. But they're careful in the beginning. The first distillation product is not ethanol, it's methanol. So they know by experience how long to wait to catch that first distillate and throw it away. Because if your customers drink that methanol, they'll go blind at the very minimum, and it could kill them. So distillation is by heating, and you convert by boiling the liquid into a gas, and then you recondense it somewhere else. That's a physical change. Filtration. We note the difference in particle size, even the states of matter. Say we have a liquid and a solid together. You can pour those through a filter, and the liquid will go through, and the solid will remain behind. Or if you have a liquid with different particle sizes in it, you can choose your filter paper so that you can remove the larger particle sizes and the smaller ones will go through. Then you can run it through, pour it through a different filter that will catch smaller particle sizes, and you can separate the smaller particle sizes too. So that's based upon the states of matter, filtration. Adherence to a surface is responsible for chromatography. If you've never seen an extract of plant leaves that are allowed to migrate up through a strip of paper, you will see them separate into colors. That's chromatography. In fact, that's where the name is derived. Chroma means color, and graphy refers to writing. So literally, chromatography is color writing. But the difference is based on how strongly the components of those colors adhere to the paper. If they're bound strongly to the paper, then they'll spend more time on the paper. Okay. So let's say we have our extract down here, and we have our strip of paper here. So we have one color here and another color there. Okay, X's and O's. Let's say the X binds more strongly to the paper. So as the liquid migrates up the paper, the X spends more time on the paper than it does in the liquid. So it stays behind. It stays low down on the paper. Whereas the circles, the O's, are not as strongly attracted to the paper. So they spend more time in the solution, and they move back and forth between the paper and the solution. Only if you spend more time on the paper, you sort of lag behind. So the circles will move faster, and you get those separated colors. That's chromatography in its simplest form. If you use the volatility of a substance, you can separate the mixtures by evaporation. So let's say you have salt water, right? It takes a lot of heat to melt and even boil sodium chloride, but not so much for water. So all you have to do is wait, and the water will evaporate and leave the salt behind. Or if you're in a hurry, you can add heat and combine boiling point and volatility to remove the water and leave the salt behind. This is just a demonstration of separating water from salt. Right? This is the container with your mixture. You add heat, the water boils, and then we condense it over here in a cold pipe, and there's the water, and the salt is in here. So you've got them separated based on physical properties. Okay. These are illustrations of those various physical properties used to perform separations of mixtures. This is just a schematic to sort of organize what we've talked about before. Matter can be a homogeneous mixture, it can be a heterogeneous mixture. By physical means, you can separate either one into a pure substance. Or the matter might already be a pure substance, in which case we bypass the mixture. But if you have a pure substance, it can be an element, or it can be a compound. And the only way to go from pure substance compound to pure substance element is by chemical means. You have to break bonds, and very often reform new ones. But the reformed bonds for for elements only occurs with the diatomics. All the other elements, well, I shouldn't say that, because some elements are not just diatomic, they're tetraatomic or octaatomic. But I'm not going to go there for you guys unless it's necessary at some later date. Okay, so that's a description, a discussion of matter in chapter 3.